So I had two things, sort of to step back and make sure I'd covered that I feel like I didn't. One of them I never talked about, and the other one I want to revisit. The first one I want to talk about was, and it's on the problem set, but I'll talk about it anyway. Which I'll remind you, the problem set's due Friday, right? I remember it this time. If you think about looking at a glass window pane, you see yourself in it reflected, of course. You see approximately 4% of the light that hit the window pane from you coming back at you from the front surface. And you see approximately 4% of that light from the back surface. So you see approximately 8% of the light that left you heading for the window comes back at you, right? And that is a consequence of the change of speed entering and exiting the glass. If you crush the glass into lots of little pieces, I mean, they're not going to be as flat as window panes and stuff like that, but basically you can imagine it being just a heap of tiny little window panes, all facing random directions. And not surprisingly, you'll still have reflections coming off that. 4% off the front surfaces, 4% off the back, and the result of that is that when your light from you goes, well, not from you anymore, let's let it be a flashlight. You shine a flashlight against it, and that light is bouncing off every surface in the heap of surfaces, a little bit from each surface. The result is an enormous amount of reflections. They go in all kinds of directions, and the material looks white. This is the origin of white stuff. Almost all the white stuff you ever see is really transparent material that's very finely divided. We saw the same effect in my discussions after Rayleigh scattering. Remember back, Rayleigh scattering shows up because these little tiny particles can act as little tiny antennas, and they're crummy for red light, but they're decent for blue light, and you get blue light scattering, the famous Rayleigh scattering. As the particles get bigger, they become antennas that are decent not only for blue light, but for red light as well. You get all the colors scatter, and you get the whiteness of a cloud. And technically that's known as me scattering, I mentioned. That's the antenna way of thinking about little particles that are transparent, but that have surfaces to bounce off of. So you can think about the sending light in every which direction indiscriminately in terms of color. You can think of that as the scattering from little antennas, or you can think of it as the surface reflections from the surfaces of these little tiny droplets. The physics turns out to be the same, they just have different ways of looking at it. I've said it so awkwardly. It's a little ball, say a little ball of a transparent material. It could be glass, it could be water, it can be anything that transmits light perfectly. You can think of it as a little antenna that scatters all the colors. Or you can think of it as a little spherical object that has front surfaces and back surfaces, and you get reflections off them. It's all the same physics, finally. Is that okay? So the public service announcement part of this is, if you want to make something that's white, put lots of little transparent particles in there. White cloth, for example, is made of transparent molecules. If you took your cotton and you squish it until it has no air gaps in it at all, so there's no speeding up and slowing down, it becomes transparent. That actually is cellophane. I think cellophane is cellulose. It's the same chemical. It's just transparent, just like glass. But having it finely divided makes it white because the light has to go in and out, in and out, and in and out of all these little gaps, and it reflects off of all of them. And if you kill off those gaps, if you get cloth wet, it becomes relatively transparent, right? White cloth drifts towards transparent because you kill the gaps off. Okay? The public service announcement part I wanted to say was paints, white paint. All the white pigments in paint, the ones that actually don't just play with color, but they reflect the light. They have hiding power. You apply a good paint over the messed up basement of the fraternity, right? You paint over, you put white paint on, the first layer doesn't cover it, but the second layer does. All the crazy whatever was there. What's sending back the light and making it look white is little particles in the paint, pigment particles. And the original pigment particles were typically like lime, like Tom Sawyer whitewashing the fence, hopefully vaguely familiar to you. The original white paints were just clear minerals, basically powdered minerals going on there, lots of little surfaces. People got smart finally and figured out how to make a better pigment. The most important better pigment that stuck around until the 1930s was lead carbonate. Great, it's a great pigment. Well, it's relatively good pigment, cheap. It has a big index of refraction, so light going in and out has a big reflection. Lead carbonate was put into all kinds of paints. That's why you got lead, the lingering problem of lead paint in old houses is there because they put lead carbonate particles in to reflect the light. Subsequently, they got better, less toxic and far better pigment particles. The pigment that's in almost everything now is titanium dioxide. It has a very high index of refraction. The light reflection off of each particle surface is enormous, and so it's very effective at sending back the light. You only need a little bit of it to get the job done, and it's in everything. I mean, you eat it too. I mean, I'm sure it's put in food. All right, and you understand why it works? Lots of little surfaces. All right, that was one thing I wanted to go at. The other thing I wanted to go back at is the idea of these quantum waves that say an electron lives in an atom. When it's sitting in an atom, just minding its own business, and you're not looking for it and trying to pin it down, it lives in a quantum standing wave known as an orbital, to distinguish it from an orbit, which is sort of a classic notion of having it whizzing around an attractive center. And when it's in that orbital, there are only so many orbitals. They're very distinct from one another because they have to do things correctly. They sort of have to as you work your way around any particular path around the nucleus, for example, and are looking at the electron's wave, it has to come back to itself by the time you've completed a full trip around. It's a little more complicated than that, but that's the basic idea. You can't have it as you go around and it waves in space as well as in time. You can't have it undergo sort of 1.5 undulations of its wave during a trip around, and you come back and it's different than when you left. If you're taking a flash photograph of this wave and you want to go around it, it's got to come back on itself. It has to line up right, which is equivalent to saying, if you look at the waves that live on a string, and I showed these to you a couple days ago, you can have this one where it's got one place at which it's moving the most, and you can have the 2/2 string one, which I can hardly do, and this is probably some stupid dance, but where it's got two points of maximum motion, what are known as antinodes. But you can't have 1.5 antinodes. The ends have to match up right. In the case of a guitar string, the ends have to be motionless. The guitar string's ends can't move. You can have a wave that's sort of this long and has one end moving. It's forbidden. So the same thing happens in orbitals. You only have very specific waves that fit around the atom, and that discreteness of the various possible states is what gives rise to these discrete spectra that I was showing you last time. Neon doesn't emit all colors. It emits only the colors that correspond to steps from one orbital and its energy, the energy associated with that orbital, to another orbital and the energy associated with that orbital. If the atom has its electron in one of these higher excited orbitals, an orbital that's not normally used for an electron, if the electron's there, it can't be in some other place where there's no orbital, because it has to have a particular home. The home has to be a specific wave. So it's in one of those orbitals, and it jumps to another allowed orbital, one that actually works. There's energy space in between these two. So I'm drawing them in space as though they're separated in height. But that's just conceptually, I'm trying to illustrate that they're separated not in height really, but in energy. The higher energy orbital, one that works, a wave that works, is the electron's transitioning to another orbital of less energy, but another wave that works. And the amount of energy that's separating these two orbitals, again in energy, not in space, comes out. That missing energy comes out. It comes out as light. And as I mentioned last time, the the energy determines, oddly enough, the wavelength and frequency of the light, as well as everything else. So to produce a photon of a red light, as in the red light of the neon sign, you need the orbitals to release about 2 and change electron volts of energy. Again, I told you an electron volt is a very tiny unit of energy, convenient for this context, because talking about joules is too big a unit of energy. And we'd be talking about the tiniest flinder of a joule. About 2.5 or so electron volts, 2.5 of these tiny units of energy, correspond to 1 particle of red light, creating 1 particle of red light, and off it goes. If the orbitals are separated by a larger amount of energy and they release that energy, it'll go off as a different color of light, a portion of light, a quantum of light, a photon of light, having a different color. And this, if it's got more energy, it's going to be more towards the blue end of the spectrum, of the rainbow spectrum. All right? So what I was trying to make sure I got across is the discreteness of the orbitals. Not all possible energies. Electrons can't have all possible energies in an atom. They can only be they have to be in orbitals, and each orbital has associated with it a specific amount of energy. And that's all they can have, those values. Any questions about atoms, orbitals of atoms, the movement between orbitals? I should say one last piece to this that will come up shortly is, just as an electron can emit a particle of light, a photon of light, in going from a high energy orbital to a low energy orbital, the electron can absorb a photon of light in order to go from a low energy orbital to a high energy orbital. It's reversible. And so in that neon lamp that I was showing you the other day, not only was it emitting red light, but on occasion, an atom over here would emit its favorite flavor of red light. Poosh, out goes red light. And another atom over here would watch that particle / wave of light come by and go, that's my favorite flavor. I happen to be in the low, I've got an electron in that low energy orbital, but if I absorb that photon going by, I can transition this electron from the low energy wave to the higher energy standing wave. And that happens. So that just as atoms are there throwing out their preferred colors associated with the energy spacing between orbitals, there are other atoms absorbing those same passing waves and doing the reverse transaction. In the case of that glowing lamp, you wouldn't notice this is going on. It's not particularly significant. The next thing that happens is the atom that caught that photon and underwent a transition to higher energy undoes that same thing. It goes back to lower energy and sends out the photon again. So you wouldn't even notice it's happening, but I'll show you in a moment that it is noticeable in certain contexts. All right? What next? All right. So at this point, where I've tried to get to in terms of discharge lamps is, you can make a lamp simply, the simplest of lamps is like the neon lamp. Simply run an electric current through neon gas. Itself a bit of a challenge. You have to get the neon gas to carry electric charge moving through it, and that involves knocking some of the charges out of the gas so that it now has charged particles in it. But okay, you get that going. You run the current through the gas. You smack into you have flying projectiles smacking into atoms and pieces of atoms and shifting electrons between the orbitals. And when they absorb energy, they store it briefly and then they send it out, typically as light. And so it's glowing with its favorite characteristic colors. This impact excitation is one way. You can have fires, burning things, high temperatures can also cause these high energy states to appear, and then they radiate away their light. And that's the basis for fireworks. So where all the colored stars and whatever in fireworks, that's all coming from the atomic emissions of burning materials that have interesting spacings between their electron orbitals. So for example, the beautiful reds that show up in a lot of fireworks is associated with an element known as strontium, which has a really intense emission between two orbitals in the red. Some of the blues are copper or barium, and green. Barium is particularly green, and so on. So the various elements they're working with to create these emissions. Okay, so that's simple discharge where you're actually looking at the atoms themselves glowing by virtue of dropping from high energy orbitals to low energy orbitals and emitting the missing energy as light. Fluorescent lamps were a little more sophisticated. The discharge itself is in a gas of mercury. This is why fluorescent lamps, in principle, should be disposed of carefully because they truly do contain some mercury. It's unavoidable. It's not like a manufacturing defect or some other thing. It is the basis for the discharge. Mercury gas is essential. But the emission from mercury is not primarily in the visible. It's almost exclusively in the ultraviolet. It's glowing brilliantly in the ultraviolet. And the ultraviolet light then hits the phosphors on the inside of that tube. And those phosphors absorb the energy. They basically have the equivalent of orbitals. We'll talk about them soon. But they're quantum states also, but they're not quantum states of atoms. They're quantum states of solids. And they have a different name, just arbitrarily. They're called levels instead of orbitals. What distinguishes them from an orbital is all about, the electron in an orbital is all about that positively charged center that it's attracted to. So calling an orbital around that center makes sense. In a solid like a phosphor, the electrons are there in quantum states too, but they're not attracted to a specific center the same way. So calling it an orbital, not such a good name. Instead, they have a different structure, and giving them another name is sensible, and they're called levels instead. Anyway, the ultraviolet light from the mercury discharge is absorbed in the phosphor. It moves electrons from low levels to high levels, high in energy, and then they drop back. But it's done strategically, so they don't just simply re-emit the light that hit them. They emit lower energy light, as in light with, it's got less energy than the ultraviolet photon. So instead of being in the ultraviolet now, it's in the visible somewhere. And they pick the phosphors carefully, so they make sure they got a good balance of the reds and the greens and the blues, and we see white light, or some equivalent of white light. And that's what you're illuminated with right now, is light that's coming from the phosphors, where they receive their energy as ultraviolet light from the mercury discharge. They then re-emit it in various parts of the visible spectrum to synthesize together what you construe as, and your eyes perceive as visible light, white light. All right? A lot of advertising signs that are not neon itself, and you saw the neon glow here, and you recognize it when you see it. A lot of the other advertising signs that have different colors, they're actually not gas discharge lamps the same. They're not like neon. You're not seeing glowing atoms. You're seeing a phosphor on the outside of a mercury discharge glowing. So they're just wacky fluorescent lamps, meaning that instead of changing the gas inside to get the colors, they stick with mercury. Mercury's good enough, and they put colored phosphors on the outside, so that when ultraviolet hits them, instead of glowing white, they glow blue or red or whatever crazy color they want to put on the inside. Is that okay? So that's it. All right, so I'm down to the last kinds of discharge lamps. Still in use, although they're getting, they'll be replaced by LEDs, which I'm going to come to. High pressure lamps. And I got two high pressure lamps. This one is mercury, and that one is sodium. Why is this anything new? Well, if you run a gas discharge through a very tenuous gas of mercury, it emits pretty much only one color, that ultraviolet thing that I talked about. But if you crank up the pressure in the lamp, so instead of just mercury, mercury naturally evaporates to a very slight extent at room temperature or a little above room temperature. And those lamps are working with just the ordinary mercury that's a vapor a little above room temperature. This lamp, not so much. This lamp actually heats the mercury up in a tube. It starts at room temperature, but by the time it's operating, it's hot. And at that pressure, at that temperature, the mercury really evaporates nicely. It's like building up steam in a steam kettle on the stove. You got a lot of mercury there, and the result is, yeah, the discharge is still going on, but collisions are occurring all the time, to the point where when you get a mercury atom chock full of energy having been hit by some charged particle, and it goes, oh, I'm going to release my favorite color, ultraviolet. Before it has a chance to do that, it may get hit again. And the result is the electron, which was already in a high-lying energetic state, ready to emit ultraviolet, gets knocked into another orbital, even higher, or even higher still. And you start getting electrons moving between orbitals that aren't normally involved in a low-pressure mercury discharge. They keep building up energy. And the result is you get a much richer spectrum coming out, including visible light. All right, so that main ultraviolet one, it's still there, but there a whole bunch of other ones showed up. The other thing that happens is that these the atoms that are trying to emit light, they often will get hit while they're emitting light. And to create a very pure, specific color associated with the energy between two specific orbitals, the transition has to be allowed to take its time. It takes time to make a wave that has a really well-defined wavelength. You want to have lots of ups and downs. I'm in a visual wave. I'm doing like water wave. For a water wave to have a very well-defined wavelength, you don't want to just go up once and then down. What's the wavelength? There's only one crest. You want it to do a whole bunch. And so you can get out your ruler and you can measure the distance between these two crests, or maybe even those two crests, and divide by 2, or 3 crests and divide by 3. So to get a really well-defined frequency wavelength, and therefore color of the light, it needs time. The more time it has, the more carefully defined the wavelength and frequency can be, and the more sharp the color can be. If an impact comes along during the emission, it truncates the time. It shortens the time involved. And with less time to work with, you have less definition of the energy. This is an uncertainty principle relationship. And I mentioned last time that in the world of quantum stuff, you often can't know simultaneously one thing and another. You can't know position of an electron, for example, and exactly what its momentum is. You can't simultaneously know exactly where it is and exactly how much momentum it's carrying. They're not defined. Another pair, and I mentioned this and I couldn't think of an example, another pair where you can't have them both is energy and time. You can't know exactly when a particle of light came out of a discharge and also know its energy perfectly. You need to give up total knowledge of the time it came out in order to get a very well-defined energy. And that smacking process is causing trouble. The impact during emission is causing trouble to that. The result is you get the energy of the light that comes out of the packet of light stops being so well-defined in an environment where there are lots of collisions. So, as I'll show you with the sodium vapor lamp doesn't produce ultraviolet. It produces its favorite yellow, and it's very intense yellow. Just one, it's actually two wavelengths. It's just, that's its favorite color. The yellows in fireworks are often sodium, because that's its color. When the lamp first starts, because sodium doesn't like to be a gas at room temperature, they put another gas in there just to get the discharge started, so the color will be wrong for the first couple seconds, and then you get the yellow, and only that yellow. But as the pressure builds up, weird things happen. First of all, you get that effect where not only do you get that yellow, but sometimes the sodium atoms, instead of just going to the upper state of the yellow and then emitting yellow, they go to the upper state of the yellow, and then another charged particle hits them and knocks more energy into them, and they start working with orbitals they wouldn't normally work with. So the spectrum gets richer as electrons start to move between the really high energy orbitals that are normally not involved in anything. The other thing that happens is that sodium, that specific sodium emission gets broader because as an atom is trying to emit that favorite sodium color, it gets hit, and that truncates the emission. It gets stopped, and the color doesn't have time to become pure. It becomes fuzzy. in energy, and therefore it comes out with different colors. So you'll see the emission spectrum get broader. I'll show you the yellow. I've been talking this to death, but okay, I'm almost done talking to death. You can wake up and watch. So the emission spectrum will get broader, just because the collisions are starting to smear out the ability to have a well-defined color. And the other weird thing that happens, we ought to be able to see, is right at the center of that smearing emission, right where sodium's very favorite color still is, the one it wants if it doesn't get hit, that part of the emission will disappear. And the reason it'll disappear is because throughout the entire volume of sodium, every atom that is not in an excited state, which is a fair number of them, is very interested in that color. That's its favorite color, both to emit and to absorb. So if an atom over here somehow manages to emit that color and not get hit during the process, and it emits it and sends it off through the thick of all the other sodium atoms, there's very likely to be one going, I haven't been hit lately, I'm in good shape, I'm looking for one of my favorite colors, oh, here it comes, it grabs it. And it takes the energy in and goes to the excited state. And then it gets smacked, and the electron moves around among all these states. And that photon never gets re-emitted. It gets eaten. So this is a process where the favorite color of the discharge disappears. And it's probably true in the mercury as well. The favorite emission becomes, there's a name for this, and I can't remember the name. It's called radiation trapping. The favorite color gets trapped, and it disappears from the spectrum because all the other colors that can get emitted do manage to escape. Nobody's looking for them. But all the atoms are looking for that color, looking for the favorite color, and it just can't get out. All right, any questions on this before I show it to you and stop talking? Or reverse that order. Stop talking and show it to you. All right, so mercury vapor first. So I'm going to light it. You'll first see it do some weird color things. Again, it's trying to get started, and in the starting process, all bets are off on what it emits, because it may have gases in there other than mercury. And what I want to do is get the right camera on this. And side projector. Yeah, okay, I forgot I even have neon. Let me show you neon here just to get it going. So there's neon. Again, we're using interference effects to separate the colors horizontally, and so you laser pointers, right? So these are discrete lines. Not every color is present. These dark spots correspond to colors and therefore energies for which there are no pairs of orbitals that have those. You can't find any of the choices. There's no mix and match where the energy difference between the two orbitals is exactly right to create, say, this yellow in the middle. Sorry, missing. You won't get any of that light. Okay, so turn off the neon, and I will turn on the mercury vapor lamp right here. It should be here. Okay, there it is. Okay, colors are weird at first. Let me see where I can get this bulb to show up, right? There they are. They're the colors that are present in the mercury. And right now there's a lot of the blue. It's the same blue that actually shows up in low pressure mercury, because the pressure is still low. It's warming up. I'll turn on the low pressure mercury. Here it is. It's that same blue. In fact, these two spectra probably can get them both. There's the same spectra for that lamp. There's the blue, the green, stuff. There they are. But there are other colors showing up. That yellow wasn't there a minute ago. That joined to the crew. So as this lamp heats up, and you've seen these lamps heating up, and that's why it takes time for them to warm up. They literally run hot, like, searingly hot. And as they're heating up, the pressure of mercury is building inside, and new lines are appearing corresponding to high energy orbital pairs that wouldn't normally be involved in a low pressure mercury lamp. This is low pressure mercury. That's higher and higher pressure. You've also noticed, in the case of seeing these lamps, that there's a power flicker, brief brownout or blackout, whatever. The lamps go out, it's 5 minutes before they come back properly. Why? Because it's really hard to start a discharge in high pressure gas, like room pressure. You know how hard it is to make a spark in this environment, right? You have them with static electricity, but that's tens of thousands of volts making that spark. To get a spark going in very low pressure, much easier. And so see, now you've got lines in here. It's all filling in. It's become a big smear of emissions. So back to the lamps restarting. They have to cool down in order to restart, which is a huge nuisance, but it's life. You've also noticed that like when the street lamps that use these kind of bulbs turn on, they initially start with those weird colors and then they drift towards this whiteness. Okay? I don't think we'll see anything more interesting showing up there, but you get the basic idea, I hope. Any questions about high pressure mercury lamps? All right, I'm going to turn it off before we all go blind and shift over to the high pressure sodium vapor lamp. So if it were a low pressure sodium vapor lamp, and I told you about those last time, it would emit yellow light, two very specific wavelengths. There's a reason why there are two of them rather than one. They're very close together. You can't tell them apart with your eye. It just looks like one color, and it's a real nuisance. And that's all it'll ever do is those two favorite colors all day, all night. This guy will build up pressure, and it'll be different. So let me turn it on. Okay, so it's starting with some weird color. I don't know what gas that is in there, but it's not. The initial gas is just a little bit of something other than sodium, and that it's not what we're paying attention to. So the spectrum here is now a mishmash. We probably could identify what that gas is by looking at that spectrum. But you can see the yellow starting to show up. There's the yellow. That's the famous sodium yellow. And it's building up, and eventually it'll take over from the original gas. And we'll start seeing a spectrum of sodium. And that spectrum will get richer and richer as the pressure builds and we get more orbitals involved. There's just more opportunity for a collision, for an excited sodium atom to get hit and absorb more energy, or to get hit while it's emitting and therefore emit a weird color that it wasn't intending. So all these other lines are showing up. Those are all, that's sodium, but it's weird. It's sodium emission lines that aren't normally present in a low pressure sodium vent. They require orbitals that don't normally get involved. And what I hope we'll manage to see is there should be a black line showing up in the middle of this bright yellow spectrum. It's getting wider in part because the camera's going crazy staring at this intense yellow, and it's just blooming. But it's also that the spectrum is actually getting wider because of impacts during the emission of light from that sodium. It's called the resonance line, and it's got a specific color when nobody hits it, but if you hit it during the emission of the resonance light, it will emit other colors smeared left and right in wavelength and frequency. And hopefully we'll get a black spot in the middle. I might have to, I don't know how to adjust the aperture on this guy. Too many controls. Can I do it? The old-fashioned way. Oh, come on. Up, down, left, right, no. It's too dazzling. I can't do it. Boo-hoo. Give myself one more try here. I can get it, but I can't hold still. I'm not a good statue. I can see the dark line. Can you see that there's a dark line right in the middle? Bunnies and flying. I want to get the dark line. give me one more minute. I'm just OCD enough to try. There's the dark line right there. In the middle of the yellow, there's a dark spot. That's radiation trapping. Again, that's because every time one of the atoms does succeed in emitting that color, there are desperate atoms everywhere else to gobble it up, and it never gets out. All right? I'll stop. It's, you can stop staring at yellow light. You notice, I hope, that the yellow light went from really yellow to kind of yellow-white, pastel-y bright, because all the other colors start showing up and it starts looking decent white. There are a lot of discharge lamps around. Actually, the projector lamps, incidentally, it's still, they probably have LED-based projector lamps at this point. But if you really want an extremely bright white light source that comes from one location, essentially from a point, which allows you to really work with that light nicely and make the projection process really clean. The brightest white lights are still discharge lamps, as far as I know. So you get at movie theaters, at least, and stuff like that. The lamp they use, these are gas discharge lamps. They run high pressure often with exotic gases like krypton and xenon. There are so many orbitals around, so much complexity to the atoms that they almost every color is represented, almost every wavelength is present. And because the light comes from such a small location in space, and therefore tremendous temperature and stuff like that, you can focus it really nicely and stuff and make a good projection process. So these lamps, the lights on these projectors are gas discharges too. Related to the ones I've been showing you. Expensive, the tubes burn out, all that stuff. Any questions about discharge lamps then? The whole idea. Okay, so I will leave discharge lamps, and the idea with all this is I'm working my way from the simplest light source, which is just a hot surface. Hot surface of the sun, hot surface of the particles in a candle, hot surface of the tungsten in an incandescent light bulb. It makes a very simple spectrum. It's called the black body spectrum. I never use that word in this class, but that's what it's called. And all the colors are present, smooth, no structure. Next more sophisticated light source is these atomic or atomic-like emissions, where you've got electrons moving from quantum standing waves to quantum standing waves, in the process giving up the missing energy as light, or alternatively absorbing energy and making the reverse movement. So everything that can emit light can also absorb light. It's symmetric. The next step to go is the sort of sophisticated synthesizing of light, as in, a laser is the ultimate light source. Really delicately synthesizing a light wave to the point where it's a single light wave rather than the buckshot I described for the light coming, say, from the sun, where every wave is independent of all the other waves. In a laser, they're not. They're all related to each other. In fact, they're copies of one another. All right, so before getting to lasers, though, I'll start with light-emitting diodes, which are probably going to be the dominant source of light probably in your lifetime, over the course of your lifetime. Most lighting is going to be LED based. And I'll try to give you an idea of how LEDs work. My question here at the front. How do the temperatures of a red LED and a blue LED compare when they're both emitting light? What do you think? How many think the red LED is hotter? How many think the blue LED is hotter? How many think that the temperatures are about the same? They're about the same. The light is not emitted for thermal reasons. In principle, you could heat them up or cool them down all you like. You will mess them up if you're a little careless for interesting reasons, but it's not a thermal emission process. It's more like an atomic emission, and it's not driven by thermal excitation to get the energy into the atoms. It's a strategic injection of energy from an electric source, from a power source, from like a battery. All right, so that's the point. Some observations about LEDs is you can, they often have very specific colors and sort of unusually pure colors. Not all of them, but many of them. They can operate for years without failing, and this is a huge advantage. Incandescent light bulbs, you can make them last a very long time. However, they will be relatively red in light because you run them at too cold, and they'll be terribly energy inefficient. So 20 years ago, I would have done my public service announcements on long life bulbs. Ooh, great, wonderful. Well, long life bulbs were energy inefficient. Yeah, you can make the bulb live a long time. You just take bulbs that were intended for higher voltage, and they would tell you, long life bulb, you look at, oh, intended for 130 volts, which is not what you use. They run too cool. They don't burn out. That's good. But they don't produce a lot of blue or even a lot of green. They're a really crummy color. All right, so incandescent light bulbs, historically they were designed to live about 750 hours, which is not a long time. And so a normal household, mine included, we'd be changing bulbs all the time. Next step forward, fluorescence. They live a lot longer, but not forever either. What's the failure mode for a fluorescent? To get the charges in and out of that gas discharge, you have to have interesting structures at the end. Electrodes, devices that are designed to convey charge into a gas and to take it back out of a gas. And those structures age, and they particularly age because of turning on and off the lamps. So fluorescents are not good when you cycle them a lot. They have only a certain number of starts in them. So if you turn them on and off every 5 seconds for some reason or other, they'll only last weeks, not years. They're supposed to last a couple thousand hours. In practice, it's hit or miss. Anybody who's had a lot of fluorescent lamps around their house, this one included, know that you do a lot of replacement. This one's a nuisance because how do you think they replace it? They have to bring scaffolding in here to get these lamps, and they're a real problem. So, next step along the way is LEDs. And there's almost nothing in an LED that can go bad. They're spec'd at living 100,000 hours typically. They do age a little bit because they have intense electric fields in them. They're very small structures. They have big voltages across them sometimes, or significant voltages, and that pushes charged thingies around. And so you get migration of some of the constituents of the LED that eventually, it usually dims rather than dies. It usually just loses its brightness. So anyway, it's a huge improvement. You all will have, in your lifetime, sort of permanent lights where you install them at when your house is constructed, and they're there for the rest of it, until you remodel. All right, which is every year, of course. So the questions we'll go after, and I'm getting pretty far along in time, so let me see if I can jump right into this story and give you something interesting. I'm not going to go to this slide. I'll just give you some pieces of the story to get us sort of to jump ahead. LEDs are semiconductor devices, in case you haven't noticed. So they're built with the same conceptual, on the same conceptual basis as building computer chips. They make use of a concept or a device known as a diode, light-emitting diode. What's a diode? A diode is a one-way device for electric charge. You can send current through it in one direction, and it will flow essentially without trouble. Try to push current the other way, and the diode will simply block it. It cannot flow. And a simple way of thinking about why there's this one-way process is, I guess, is to think of a river with a waterfall in the middle. If you have in a real waterfall, of course, the separation involved here is an altitude one, which involves gravitational potential energy of the water. Water is not likely to go spontaneously up because that requires gravitational potential energy. So if you try to push water through a river system that has a waterfall in it, you can get the water to go from the high side. You can put water in on the high side have it fall down the waterfall and come out the low side. That'll work, right? If you try to send water through this system, sending it in on the low side and having it jump up the waterfall and go out, ain't going to happen. And that is basically going on in a diode. Same idea, except it's not in altitude, it's in energy. You're going to be, we'll be pushing in electrons. And now we have to pay attention to the fact that they are actually are electrons. They're negatively charged, but that's life. They come in at high energy, in quantum states at high energy. They drop down the waterfall, and they leave at low energy. And that's a one-way system. You can't go backwards. In a conventional diode that's used simply to force current to go only one way, that dropping down the waterfall is boring. They just drop down. They lose energy in the process, but it just turns into thermal energy. The same way water going down a waterfall, it loses energy too, becomes thermal energy in a waterfall. It's warmer water at the bottom of the waterfall. In a light-emitting diode, that drop down the waterfall from high energy to low energy, the energy that's involved each time an electron drops, about 50% of the time it goes out as light. And so the light that's coming out is the energy associated with the drop from high energy to low energy and crossing that waterfall. It's called a PN junction. We'll come there. So just for fun, as time has gone by, in the old days, my only choice is to show you, do I know which one's which? Probably this and this. I could show you light-emitting diodes. Since I got a minute more than I expected. Is that the right? Oops. Here. I can give you colors, right? You see colors, right? But it's kind of dim. This is not impressive, okay? Now that they're starting to like make highway lights and stuff using LEDs, you get these rather more powerful light-emitting diode sources. So here I've got 4 little 9-volt batteries. That little guy. Can you believe? I got more. Sorry, I have to put it back up because it's so cool. That you can get that much light from a package this dinky. I can't believe it. It's so great. Like now you all have like a square glow for the rest of the day on your eyes. But this would have been unimaginable when I was a kid that you can get that. All right. By Friday, end of Friday, you'll understand why that worked, okay? At least I will give it my best shot.